rim contact mounted lens. So in this kind of contacting method, we use the rim of the lens for putting it into the lens cell or the lens barrel. In this kind of scenario, we have a minimal clearance between the outer diameter of the lens, which are these two edges, and inside diameter of the cell. It can be around 5 micron. As you can see in this animated 3D model, we have a perfect lens and a perfect lens cell. So in this scenario, when we have a perfect lens and perfect lens cell, the mechanical axis of the lens, which is in this scenario is the mechanical axis from the outer diameter of the lens cell, and the optical axis of the lens can be perfectly aligned. We can have another scenario that the lens itself is not made perfectly. So the lens is tilted during the grinding process. So in this scenario, we have a perfect lens cell, but the lens edge is not aligned very well to the optical axis of the lens, that the end result can be a lens that is not optically aligned. I mean, the optical axis of the lens is aligned to the mechanical axis. As you can see in this photo, the lens is tilted, and the end result of this kind of situation is that the final image is also tilted and the beam that is passes through the lens is tilted. So that causes aberration to the system. We have another scenario that the mechanical axis of the cell and the mechanical axis of the lens and optical axis of the lens, they're aligned, they're parallel, but they're not coincide completely. So we have an offset between these two. As you can see in this photo, in this animated 3D model, the top edge is thicker than the bottom one. So in this kind of scenario, we have at the end result is that the image is tilted because the mechanical axis is not aligned with the optical axis. Even they can be parallel, but the end result is that the image get tilted. We can have another scenario that the lens is perfectly made, is perfectly centered, grinded. The mechanical axis of the lens is aligned to the optical axis of the lens, but the associated mechanical parts for a rim contacted mount are not correctly made. Like in this scenario, you can see the datum B, which is the outside diameter of the cell, is perfect, but the datum A, which is the outside diameter of the lens that contacted to the inside diameter of the cell, is not aligned perfectly to datum B. So the lens itself is perfect, but the mechanical intermediary medium between the lens and the barrel is not aligned perfectly. So in this kind of scenario also it causes the image get tilted, and datum C, which is the seat for the lens, is also perpendicular to datum A. That one is also tilted. So in this scenario also we have a mechanical axis of the lens which comes from the outside. Lens itself is perfect. The mechanical axis of the lens is perfect, but the whole system, which consists the lens and the cell, is not aligned well. So again, we have a scenario that the mechanical axis is not aligned with the optical axis. We can have another scenario that the mechanical axis, datum B, which is the outside the diameter of the cell, is aligned perfectly with datum A, but again, we have an offset between the centers of these two. You can see the thickness on the top is much higher than the thickness on the bottom. So this scenario also cause a tilt in the final image. So the mechanical axis is parallel to the optical axis, but we have offset between these two, or decenter. Another scenario, you can have a perfect cell and a perfect lens, but the spacer is not made well. Like in this photo, you can see the spacer. We have a spacer between the lens and the cell, and the spacer on the bottom, the thickness is higher than the thickness on the top. So we have a gap here. So in this scenario, because the lens is getting reference from the edge, we have even the datum C is tilted, but datum A and datum B are parallel, and the mechanical axis can be perfectly aligned to the optical axis, but The main problem with this kind of situation is that because of the non-uniform distribution of the preload on the lens, because one side is touched by the spacer, the other side is not touched, that can cause unsymmetrical stress buildup to the lens that can degrade the final image using this kind of, I mean, this lens. For resolving all of these issues that, when you have a perfect lens, but you don't have a uh, perfect cell, or you can have a non-perfect lens and put it on a non-perfect cell and align them together by machining. For resolving these kind of issues, Trioptics, they have a machine that, as I mentioned in another lesson, you can align the optical axis of the lens using a laser getting reflection. When you align the optical axis, then you can machine the lens. You can machine the cell separately. Right now, the spindle of the whole machine is aligned to the optical axis, and then you machine the cell to make it parallel. I mean, the outside diameter parallel to the spindle, which is the spindle is parallel to the optical axis. And at the end, you can have a system, you can have a lens with the cell that the mechanical axis of the cell and lens together are aligned to the optical axis. So those are the reference that I use. Thank you very much.